Okay, this is an RLC series impedance for sinusoidal steady state. So we've got this is a sinusoidal circuit, so it has a polarity plus minus, and that polarity is, strictly speaking, it's flipping because it's a cosine function. But this is our reference polarity. So like at 0, it'll be positive here, and then 1 period later it'll be positive again, and at halfway through the cycle it'll be the signal will be inverted because it's a sinusoid. But we need to have a reference polarity on here. But it's a sinusoid, okay? Flipping back and forth. So we've got these terminals A, B here. And we've got a resistor, then we've got a cap, and our inductor, and then we've got a cap. And these have values. This is a 32 millihenry. This is a 5 microfarad. And this is a 90 ohm things. And we're given this time domain signal for the source is 750 cosine 5000 t plus 30 degrees. Okay, so it's got a angular frequency of 5,000 radians per second, and it's shifted. So the peak shows up 30 degrees before the y-axis, and the peak value is 750. We want to find the frequency domain, or I say freak domain, the frequency domain equivalent circuit, which is useful. This is a time domain circuit right here, right? This is given as ohms, which, well, that won't change. But see this 32 millihenries? That will, that's inductance. We'll have this is time domain inductance, and this is time domain capacitance. We're going to convert to frequency domain impedance and frequency domain impedance for the cap and the inductors. And so B, we want to solve for I of t using phasors, right? So we want to go from time domain to phasors, use Ohm's law in this case, and then convert our our I phasor back to time domain. Okay, time domain to frequency domain, then back to time domain. So C will be the frequency domain of Thevenin equivalent frequency domain with respect to terminals A, B. So what is the Thevenin equivalent seen by the source, really? All right. So part A, we have this formula for impedance in an inductor. It's just J omega L, right? So it's J omega is 5,000, L is 32 times 10 to the minus 3. It's going to be J 160 ohms. All right. Then the impedance in a cap, we have a formula that's J over minus 1 omega C. So it's J over minus 1, 5,000 is omega, and C is 5 times 10 to the minus 6. It's going to be minus J 40 ohms. And V, we can convert our time domain voltage signal to a phasor, frequency domain phasor. 750 is the peak, and the phase shift is 30 degrees in this volts. So that means the frequency domain circuit is going to be the 90. The resistance just comes straight across as resistance; it doesn't change. But the impedance becomes J 160, and the capacitance becomes minus J 40 ohms. This is the inductor. It's positive imaginary term, and no real component. It's just an inductor. This has a negative imaginary component and no real component. And this has just a real component, right? That's the way these things look. So this is the answer here for part A, this thing. This is the frequency domain equivalent circuit, or phasor domain equivalent circuit. All right, so part B, we want to find I of t. So we're just going to we could use Ohm's law. So V phasor equals I phasor Z phasor. If we had Z equivalent, then if we had the total Z, we could find this. So there's Vs here, and this is Is. If we had the total Z, we could solve for I. So so we need total Z, which we're going to need for the Thevenin. That would be right. This question here is a little bit worded funny. Part C. Anyway, the Z equivalent is going to be just add up the Z of the resistor plus the Z of the inductor plus Z of the cap. So impedance for resistor is just the same as the resistance for the resistor. So it's just 90. And then this inductor thing is J160, and the capacitor is minus J40. Okay, so this is 90 plus J120. And that's that's rectangular phasor. We could convert that to polar phasor. My calculator just does that, and so it's 150 angle 53.13 degrees ohms. So we could do Ohm's law now and solve for I phasor. It's just going to be V phasor over Z phasor. It's going to be 750 angle 30 over 150 angle 53.13. And once again, your calculator should be able to work these out in polar format. You don't want to be going to rectangular format with all the J's and then doing all that algebra. It's way too much. Figure out how to make your calculator do this, and your calculator should spit out 5 angle minus 23.13 degrees. So that's I. Okay, and so that's I phasor, which they didn't actually ask for. They asked for I of t, but we can go back. So I of t is, you just unplug this, is going to be 5 cosine 5,000 5,000 t minus 23.13 amps. This is the actual answer that they're asking for. And then they want to know frequency domain Thevenin equivalent. This is with respect to AB. This doesn't really make sense with respect to A. What they're asking for really is that really, just a voltage source and a resistance. Yeah, it's a funny, it's kind of an ambiguous question there. Good enough. So this is part C. Let's see. We could graph this. We have V of time and I of time. What do those look like? So V leads the x-axis by 30 degrees. Something like that. Ugh. This is 30 in here. Okay. And I is minus 23, so it's ahead by by 23 degrees. Note that the difference between these two is 53 degrees. It's the impedance. That's the phase shift of the impedance. So, so that's what impedance tells you. The phase shift or the angle component of Z, it's really telling you the distance, the shift between the I signal and the V signal. That's what it's telling you, which is most of the time what we're interested in. We don't. This 30 is just kind of an arbitrary. 30 is reference to the y-axis, which is it's just a reference. Likewise, this 23 is also reference to the y-axis. Like, they don't mean anything by themselves. What they mean is, you know, what we're interested in is how far apart are these two guys. So they're 53 degrees apart. So remember, we had a problem before where if it was so there's Eli the Iceman. If a circuit is inductive, then the voltage is going to be ahead of the current, and if it's capacitive, then the other way around. The current current is going to lead the voltage, but by exactly 90 degrees. If it's purely capacitive, if it's pure capacitive or pure inductive, these leads will be 90 degrees. But this circuit here, it has an inductor and a capacitor, so it's not purely inductive. It's not purely capacitive. It's this much. Wait a minute. It's this much. 53 degrees impedance. It's positive, so it's most. I mix these up. Eli. Voltage comes first. I think I mixed these up. And okay, yeah, I did have it backwards. So if it's purely inductive circuit, then the voltage will lead the current by 90 degrees. And if it's purely capacitive, the current will lead the voltage by 90 degrees. It's a little confusing because of when the way it, it's backwards, sort of, from what you might intuitively think. Because when you draw the sinusoids out, the V it comes first if you're going from left to right. But if you're thinking about at zero, who's there first, it's kind of sort of backwards. So that's a little bit confusing. But anyway, it's the way you draw it. The time signals, V will be first for inductive, and I will be first for capacitive. Even though that's kind of the opposite of what's happening on the, for time, right? Like at zero, V is there, and we're still waiting for I. So it's kind of backwards, but it's terminology a little bit. So anyway, keep that straight. Yeah. So this circuit here has 160 value for the inductance and 40 value for the capacitance. So it's more inductive than it is capacitive, right? So that ends up, it's exactly 120 impedance. It's a positive value, so it's more inductive than it is capacitive, and the angle's positive too, and V is So overall V is ahead of I, but it's only ahead by 53 degrees, okay? Not 90, which would be the case if there were no capacitance at all. All right,